start. All right, so the stream is starting. Penelope, can you put the shut the first set of lights? No, you're not watching it. I'm recording the stream. Okay. Yeah, it's recording right now. Okay. No, you're not in it. I'm in it. And maybe Captain America might make an appearance. But you may say hi.
Hello.
Hi. All right. There you go. So, Captain America, you're going to make an appearance?
Oh, sure.
Sure. Okay.
Do it.
So we have Captain America in class today.
Oh my.
So you can come make a stand in front of the thing.
Oh yeah.
We can't see very well, but yeah, turn the light on, Penelope. We might be able to see better. There we go. There he is. All right. Okay. So. All right, so this is the Icy Hot Lab, a post discussion, and you guys can watch this on YouTube. All right, and Patricia, we think so. We're going to take. You guys have not had a chance to really plot your points. Whoops, but you will. All right, and of course this isn't going to work now that it's broadcasting. Okay, so what we're trying to do with this lab, okay, you got collected all your data, but what we want to find is the total amount of energy. So this is basically our problem. We want to find the total amount of energy. And energy we're going to calculate as Q. That's a Q. All right, total amount of energy that was needed to melt the ice okay, and bring it to a boil. All right, and so for those of you that already graphed it, when you look at your graph, what you should see are three distinctive parts to your graph, okay? And when you think about it, when you started out with the gathering your data, all right, what did you notice when you first started gathering your data? I'm going to switch to a new page, maybe. Okay. What did you notice when you first started gathering your data? Did it go up quickly right away?
No.
What did you notice?
Slowly accelerated.
Okay, so it slowly increased in temperature. Did you notice anything odd about that part when you first were starting? Look at your data. Did it start just increasing? Oh, it was going up and down. Okay. Yeah. And so that was probably something that you did not anticipate because you kept adding energy to the system, right? So if you're adding energy to the system, you would expect your temperature to just keep increasing instead of going down. But you probably saw something like this. So I have my time on the bottom. All right, I have my temperature over on the side. And I'm just going to put in I'm going to put in some points here. So we might have seen something like this, and then we saw an increase, and then we might have started seeing a little bit of that again. All right, so look at your data. Did you see something like that? Okay, when you got to the boiling part, did you see it go up and down ever so slightly?
Yeah.
Okay, so we saw that down here. And we saw it up towards the top. So when you plot your data, we're not going to connect the dots, all right? So instead what we're going to do is we're going to draw a trend line. So basically what we saw down here, even though we saw it go up and down and up and down and up and down a little bit, the temperature remained fairly constant, okay? So when you draw this line, you're going to look at what looks like the average of that up, down, and we're going to draw our trend line so it looks like it's constant. all right? Then we have that increase in temperature, and then we're going to plateau out again. That is what a typical heating curve for water looks like, all right? Now, key thing is, remember I said I want you to make observations, okay, of what states of water you have at temperatures. So at this part right here, where you have this first plateau, what states of water did you see? Was it all solid? Was it a mixture of a solid and a liquid? Was it all liquid? Was it a mixture of a liquid and gas? Solid and a liquid, all right? So at this point right here, we had a solid and a liquid. Oh, so what was happening there? What process? Phase change. Melting. All right. So we had melting here. All right. And now we saw, so at this point right here, where we saw that increase in temperature, what phase did we have there?
Liquid.
Good. That was all liquid, right? And so now we had all the particles in the liquid state. We keep adding energy to the system. What's happening to those liquid particles as we're adding energy to the system? They are going to, not yet. They're going to move faster and faster and keep gaining more kinetic energy from that transfer of heat from the Bunsen burner, right? Okay. Until we get to this point right here. Now, at this point right here, where you start having another constant temperature, what did you see in the beaker then? Bubbles, which was?
Water vapor.
Water vapor and a liquid. So at this point here, you had a mixture of a liquid, all right, and a gas. And what process is that?
Evaporation.
Evaporation. So what can you say when you have a heating and or a cooling curve, because we can go in the opposite direction with this. Those constant temperatures represent what? Melting and evaporation is what? Physical change. You have phase changes, okay? Solid to liquid, liquid to gas. If we were going in the opposite direction, we would see condensation and freezing. All right, so every time you have that constant temperature, you have a phase change. When you have an increase or a decrease in temperature, how many phases do you have? You only have a single phase, okay? So we're either heating those particles up so that they increase in kinetic energy. There's a direct relationship, I said on the video, between kinetic energy and what else? If you have an increase in kinetic energy, you have an increase in
Heat.
not heat, temperature, okay? So an increase in kinetic energy, you have an increase in temperature. Now, let's take a look at, because on those plateaus, you actually had an up, down, you had an increase and a decrease in temperature, okay? And we should have seen kind of like a zigzag like that. So here's what's happening. We're starting with the solid, and our solid is packed very closely together, right? And it has a certain amount of kinetic energy. And so as we add heat to that system, what's going to happen to those particles? Yeah, those particles are going to speed up, right? To the point where some of these particles then are going to leave that solid and they're going to go into the liquid state, all right, increasing their kinetic energy. Well, if they increase the kinetic energy, that also increases what? The temperature. We see a rise in the temperature, but here's what happens. These particles are in constant motion, so these particles are going to come back over here, all right, as they're moving around randomly, they're going to collide with those particles in the solid, transfer some of their energy, and remember, how much energy you lose is going to be gained by the other particles, right? But these particles in the liquid state are going to lose some of that energy. Why don't we put that here? Going to lose energy to the solid particles not enough so that those liquid particles go back into the solid state. They're going to remain in the solid state, but with less energy. So if they have less kinetic energy, what happens to the temperature? Goes down. Okay, and that's where we see the decrease in temperature. They're going to go up again because we keep adding energy to the system. And so more particles are going to increase in kinetic energy, leave the solid phase, go into the liquid phase, move around with a greater kinetic energy, collide with more particles, transfer energy, temperature goes down. And this keeps going on until all of the particles at this point right here are in the liquid phase. Once all of the particles are in the liquid phase, now we start seeing a rise in the temperature. Okay, does everybody get that? Any questions with that at all? And the same thing happens up here with evaporation. Exact same thing, all right? But we don't see as much of temperature fluctuations as we do down in the melting phase, okay? Any questions with that at all? All right, so that's what takes place, okay, with this part of the graph. Now we're going to go to the calculations. So here's the thing. We want to know the overall amount of heat that was needed to go from the solid and then to boil up here for 5 minutes, okay? And so we're going to break this graph up into 3 parts. We are going to call this part right here, all right, where we're melting, we're going to call this Q1. Remember, Q is heat, all right? It's the amount of heat. So Q1 is the amount of heat that is needed to melt that ice, okay? We are going to call this middle part Q2. And Q2 is the amount of heat that's needed, okay, to go from this temperature to this temperature. And then this last part, we're going to call, what do you think?
Q3.
Q3, there you go. All right, so we have Q3. All right, now the total amount of energy, so we're going to call that Q subtotal, is equal to Q1 plus Q2 plus Q3. I'm going to start with Q2 first because you're actually familiar with that equation, all right? You use that with the Bunsen burner lab. So Q2 is equal to MC delta T. Remember that? It was in the video also. Remember that equation? Yeah. Okay. You know what the mass is of your sample, right? All right, I'm going to put in temperatures on my graph, which are basically perfect temperatures. So we all know that ice is going to melt at what temperature? What's the freezing point of water? 0 degrees Celsius. So the melting point and the freezing point of water is 0 degrees Celsius. All right, and then what's the boiling point of water? 100 degrees Celsius. Now yours isn't going to be, this would be a pure water. Yours isn't going to be exactly 0 and 100 because you use tap water, and tap water has a lot of guck in it that affects the melting and the boiling point, okay? So that's why you never got up to probably 100 degrees Celsius. Did you question that?
Yes.
That's why, okay? And we'll learn about that much later on down the road. All right, second semester. So we have this information here. My mass is going to be equal to 65 grams. All right. So all we need to do is to put in the numbers. So we have 65 times the specific heat of water. Now, if you look on your constants, you have 2 specific heats of water. You have one in the liquid state. You have one in the solid state. All right. My water at this point right here is in what state? Liquid. So what do we want to use? On your constants, we're going to use what? 4.18. All right. So it's 4.18. We have units. Now this is grams here for my 65 for my mass. And then the units for the specific heat is joules over gram degrees Celsius. All right. Now, notice that grams is in the bottom of this fraction here for the units, and I have grams here, so I can cross grams out of the equation. Now, my change in temperature, remember what change in temperature is? Change in temperature is equal to your final temperature minus your initial temperature. Well, my final temperature is 100 degrees. My initial temperature is 0, so my change in temperature is what? 100. Okay, it's 100 degrees. So we have 100 degrees Celsius. Degrees Celsius is going to cancel out. That's leaving me with the unit of joules. And in video lesson 9, I talked about heat unit, 2 heat units that we use, calorie and joules. Okay, so calculate that. And what is Q2? Are you calculating, Veronica? No, you're waiting for others to do it, right? What is it?
27,170.
27,170 joules. Okay, so that's Q2. Now take a look at Q1. Do we have a change in temperature here? No. So if we had a change in temperature, our heat would be equal to 0. Well, we know the heat needed to melt the ice wasn't equal to 0 because we kept putting heat into the system. So we're going to use a different equation for this. Look on your constant sheet. I have it on there. Okay. So for the melting and freezing phase, we use this equation here and always use this equation. Q is equal to the mass times H sub F. Now, H sub F is called the heat of fusion. It is a constant. And every substance has their own heat of fusion constant. Of course, we're using it for water. But it takes into account the steady temperature, okay, of that phase change. All right. So we're going to put in our mass, which is 65 grams. And then the heat of fusion, which is what? The constant for heat of fusion is above. Is what? 334? All right. It's right on that energy constants. Okay. It has H sub F for melting and freezing, and that's 340. Now this is joules over gram.
334. Oh, she wrote that.
Yeah, 334.
She just said it.
All right. So, what did I say?
340.
So grams divides out. All right. And then we're going to calculate that and get what Q1 is. So anytime you have these plateaus, you can't use the Q equals MC delta T. You either have to use the heat of fusion when you have melting and freezing, or you have to use heat of vaporization if you have evaporation or condensation. So what did we calculate this to be? 700 what? Okay. Good. All right. So that's Q1. Now we're going to go up here to Q3. And this is evaporation. So we have to use the heat of evaporation. So Q3 is equal to MH. Now it's sub V. Okay. Does everybody see H sub V on there?
Yes.
Okay. So that's the heat of vaporization. And again, our mass hasn't changed. So we have 65 grams. Now we're going to multiply by the heat of vaporization, which is what, 2,260?
Yep.
Okay, 2,260 joules over grams. What divides out? Grams divides out. Calculate that, and that will give us our Q3. And that should be something like 100 and some thousand joules.
So we should be using though like our own mass.
You are going to use your own mass.
Right, okay.
You're going to use your own temperatures. Okay? I'm just giving you my data. Okay, which is perfect, Ava. All right, so what do we get for Q?
146,900.
Good. All right. So that we have our Q3, our Q2, and we have our Q1. You are going to add those three numbers together to get the total amount of energy that was needed in this process. Yeah, it's going to be a big number. Probably, well, we know it's going to be over 146,000. Just saying. So we're gonna add all of those together.
That took me a second to get. I got it.
You got it? Yeah, see, I told you I'd make you smile today.
Thanks. I appreciate it.
All right. Did we get that, what that is? Elizabeth, you're my go-to girl. You get it?
195,780.
That, my friends, is your final answer.
That's fun.
And that is what you are going to do
All right.
to wrap up your part of the lab. But listen, the only thing that I want you to do for homework is that graph. So I want you to come in on Monday, have that graph done so that you can do this. Now I'm going to have a write-up for you, a paper. I'm going to actually give you paper this time. So you're going to do your post lab on that paper, all right, and turn that in. But I also want to kind of go over some of those specific heat problems also, and then give you Monday and Tuesday to work, okay, before we have a quiz, which we'll have that on Wednesday, okay? Any questions at all? All right, so you guys have 5 minutes. You can do it.